Recording is rolling. It is Tuesday, September 9th. So I have a couple of warm-up projectile puzzles for you guys from this book we'll look at pretty soon here. These projectile puzzles from last few days we've been working on. I'll see if how much time we have by the end of class today, and if we have any spare time, I'll work more these with you guys. Okay? And these are, of course, due on Friday. And then Friday is going to be your quiz on kinematic motion, which is both linear motion and projectiles. But because it's all the same equations, because no, it's all just these equations, and we're doing some practice every day, so we'll do more practice today. Okay? Keep in mind for projectiles, you have to narrow this down. What's going on strictly vertically from what's going on strictly horizontally, right? Because gravity only pulls which way? Down, which is in the vertical direction. So if you're set up a vertical type equation, then it's allowed to accelerate in the gravity field. But horizontally, there's no acceleration, so it's always just x equals vt horizontally. Okay. All right, so it's a little review there, little tidbits. Okay. Then tomorrow, can you guys dress to go outside tomorrow? Want to do a projectile lab with the guys, as long as it's not raining. So tomorrow, you guys get this projectile launcher. Ooh, this is exciting. I have a picture of what we're doing. It's pretty much this right here. Can you guys tomorrow take a meter stick and walk up the stairs and measure the height of the balcony out here? Okay. Because what we're going to do is this we're going to take this little bouncy ball, this little squishy bouncy ball. We're going to put this inside the launcher and then aim it horizontally. It's going to land somewhere on the ground below. Then you can take either a meter stick or a trundle wheel and measure how many meters out it landed. Okay. Now, if you know the height of this ledge, the horizontal displacement, the landing point of the ball, and you're also allowed to know Earth gravity. You guys know, call it 9.8 meters per second squared, or 10 meters per second squared, if you like. Okay. Do you guys think that in principle there's enough information there where you can calculate the firing speed? Can you do that? Yeah. Okay. Actually, one of the warm-up questions today is going to look a lot like that. So if you get the warm-up question, then think of the principles. Okay. So here's your launcher. Now you can adjust the angle on this launcher. Oh, look at that! I can adjust the angle. And oh, what is this? Ooh, I got a little paperclip weight on a string, and it could, because if gravity's pulling like this way, could this paperclip? It could hang through an angle on this protractor. Oh, look at this! Right, guys, that's 30 degrees relative to what? The horizontal or the vertical? Horizontal. Yeah, horizontal. Right. If I make this exactly horizontal, then this hangs through zero, as in 0 degrees. Here, get that close to the cannon. I see that hangs through 0 degrees, 0 degrees from the horizontal. Okay. As angles in this class are always relative to something. So you can measure to 0 degrees from the horizontal. That means that it is horizontal. Okay, like that. Okay. Now, here's a technical detail. Is where's this ramrod? Oh, do I have? Aha! Ramrod. Now, if I push this little squishy bouncy ball, which didn't even come with the set, if I put this in first and then I ramrod it to see this little spring right here? Can spring boing boing boing. Oh, guess what? Guess what gets jammed inside the launcher? Little squishy bouncy ball, and guess how hard it is to get out? Let's say very very. It takes a long time to get out, and that's not very fun. I think it's a lot more fun to be blasting this off the balcony. So, guys, do you want to make sure you guys are following? Do you want to put in the ball first and then ramrod it and get it stuck? Or do you want to ramrod it first and then put in the ball after the fact? Yeah, how about that last thing I said? Okay, I'll demo this for you guys. Okay, I got a real stiff spring here, so I'm going to ramrod this. Now listen real close, you can hear it click. You guys hear it click? All right, so now it's ready to go. So now I can put in the ball and I can pull this and it'll go fly it. Oh, wait, what is this? Short range. Medium range, long range. All right, can we get more clicks? Right, listen. There's 2 clicks. I want to do long range. Oh, did I just break that? Well, we're gonna find out. I don't know if this is gonna go. We're gonna see. I got 3 clicks out of that somehow. We're gonna see. Let's see. Oh, it still works. No, it's definitely good. Oh yeah. Oh yeah. So that'll be tomorrow's adventure right there. Tomorrow. Have you guys create a table where you can record these values, right? This height, this spot distance. I guess you could do multiple trials, but they should ideally. There's not really an independent variable on this, right? It's just you want to figure out like what's the blast speed basically. Okay. Speaking of that, one of my warm-up puzzles just so happens to be basically the same question. I got a boy on a tower. 4.9 meters. Can you basically call that 5 meters, maybe? Right? But maybe there's a reason they went with 4.9. Right? Because all the questions out of this book are supposed to be kind of like stripped down to some concept. Right. He throws a ball straight horizontal, and it lands 20 meters down range. So 20 meters from the base of this tower. Question is, how fast was he throwing that ball? What's his pitching speed? Go ahead and figure that out. Maybe you guys can work with each other. Give you guys a little time to think about that. See if somebody can solve that before we start going over it. He's basically on a 5-meter tall tower. He throws the ball and it lands 20 meters away from the base of the tower. You guys do recognize that's pretty much exactly your lab tomorrow. Like, what's the pitching speed? What's the blast speed from launch? It's the same question, basically. Okay. And you also know all the equations you need to solve anything like this come off this page here. Okay, or this poster hanging from memory. From a ceiling. And guys, if we're talking about projectiles, there's going to be some horizontal aspect, like I see it went 20 meters. There's also going to be some vertical aspect, like something to do with this 5-meter drop. Are there going to be separate equations? Yeah, right. Okay, get you guys thinking on that. Give you guys another hint. You do see he's throwing it straight horizontal.
Yeah.
What if instead he just dropped a ball? Which would hit the ground first? Same time. Huh. Which might have something to do with vertical type motion. Right? In fact, would that be really nice to know? Like how much time this whole process takes? Right? Which wasn't given and wasn't asked, but maybe that's a good middle question to answer. Maybe before you answer this question, you have to figure out how much time that whole process takes. Which would be identical to if you just dropped the ball. Huh. How much time does it take to fall 5 meters? It's not half a second.
The answer 20 meters per second.
That's it. Yeah. All right, Bruce got it. 20 meters per second. That's how fast he threw it. 20 meters per second. Because, guys, to fall 4.9 or 5 meters, here we go. Okay. You guys remember this? Go to the edge of a very tall cliff, and in 1 second, it will have fallen 5 meters. The ball will fall in 5 meters, right? Which is vertically identical to this. Remember, if he just drops the ball, it takes the same time. Right? Well, here it says 4.9 meters. Here I've got 5 meters. But it's really the same thing because it's like a rounding error. Guys, which equation links distance and time in accelerating environment? First, second, or third? Yeah, definitely this first one. It has here. Guys, could this generic x like displacement you could replace with the height, like the vertical height of the tower, the height of the cliff? Okay. And if you drop the ball, then what's the v naught equal to? Zero. Right. What if you throw the ball really fast to the right? I mean, that's what he's doing. He's throwing the ball really fast to the right. Is this still zero?
No. Yeah.
Yes, it is, because we're crafting a vertical equation. And vertically speaking, how fast the ball leaving his hand? Zero. It's not moving up or down at all. It's moving really fast to the side, but that's a separate question, right? But vertically speaking, it's identical to if you just drop the ball. So this term goes away. And the height of the tower is just 1/2 gt squared. Right? Now, if you plug in, you can plug in 10 meters per second squared, or you can plug in 9.8. You guys know I'll accept either one. Right? Same thing with AP, by the way. AP also accepts either one. Okay. So, guys, what's half of 10? 5. What's half of 9.8? 4.9. Okay. So to fall 4.9 meters, and if this is 4.9, you guys see that if you solve for t, it comes out in 1 second. Right? So solve for t. I guess that's actually, you know what? That is this right here, isn't it? I just almost forgot about this one. Is that the same thing as this? Yeah, same thing. Okay, now that's the first half of this. Guys, this whole process takes 1 second. If you drop the ball, it takes 1 second. If you throw this to the side kind of slow, it takes 1 second. If you throw this to the side really fast, it takes 1 second to reach it. It takes 1 second from the top of this tower, as long as he only throws it horizontally. Okay. Now let's switch over to horizontal. And horizontally, guys, is there any acceleration horizontally? No. Because gravity doesn't pull horizontally. Gravity only pulls straight down. And we're ignoring air drag in this class. We're saying, well, that's negligible. Okay? So we're getting rid of that. So these bottom two equations aren't super helpful. They just, if you get rid of A, it just turns like this. Right? Okay, great. Speed stays the same horizontally. Okay? But the first equation, okay, if this A goes to 0, now we're starting over. We're saying how far across, this is a horizontal equation. It's just V times T. Okay? And the ball went 20 meters across, and it took it 1 second. So can you divide the T down and get 20 meters per second right here? Yes, it? Yes, it? Okay, so that's the answer, 20 meters per second. Okay. Keep in mind, that's as long as he throws it horizontally. Guys, what if he pitches up at like 30 degrees? Would the ball land like maybe way out here if he pitches it up 30 degrees? Move it a little off the page. Okay. Now that would be trickier to work with because, that looks like these puzzles on the back side of this page, doesn't it? Page that's due on Friday. Okay. And I help you out here. Say step by step by step. You have to break into components. You would run into a quadratic equation at some point. Okay? And I gave you a big hint right there. At some point it turns quadratic. Okay, so let's see if we can fit that in after the Kahoot, possibly. Okay. So you guys get there? I do want to do one more warm up. The monkey, the zookeeper with a rubber band gun. Look at the slingshot right here. Oh, it's got a banana. Ooh, yeah, get that banana to that monkey. Devises a rubber band gun to shoot food to a monkey. So a banana to a monkey who's too shy to come down from the trees. If the monkey does not move, so the monkey's just hanging there. Should the keeper aim above, at, or below the monkey? What do you guys think? Who says above? Who says above the dash line? Yeah. Right. Now, if he shoots it really fast, you guys think it'll create a really shallow parabola that almost looks like a straight line, but is actually a little bit of a parabola? Yeah. Right. What if he lobs it kind of slow? Boing. Could he aim like way above? He goes boing. Makes like a more obvious parabola, maybe something like that. Okay. But he always has to aim a little bit above the monkey, right? Unless of course you turn gravity off. If you turn gravity off, then you should aim straight at the monkey. But with gravity, always aim above and make a parabola shape. Right. Right. Now here's the tricky one. You guys ready for the tricky monkey question? Tricky monkey question. If the monkey lets go of the branch at the instant the keeper lets go of the banana, so they let go at the same time. Then in that case, should the keeper have aimed above, at, or below the monkey? So the monkey catches the banana in midair. So that's part of the constraint here. Is assume the monkey gets the banana before he hits the ground, which actually makes this a lot easier to solve. Okay. Okay. So, all right. So they both let go at the same time, and we want the banana to get to the monkey again while he's still falling. Okay. So think about that for a little bit. Let's see, show hands. So you got 3 options. Should the keeper still aim above the monkey in that case? Should he aim at the monkey? Should he aim below the monkey? And how's he going to get that banana to that monkey? You guys ready? All right, see, show hands. How many guys say he should still aim above the monkey? Who says still aim above? Oh, nobody says that. Who says he should aim right at the monkey? Right at the monkey. Okay, that's got some votes. Who says he should aim below the monkey? Okay, that's got some votes too. It's about a 50-50 split. Right? Okay, so the answer is he should aim right at the monkey. If you said at, then yeah, winner. Right, I'll show you guys why. Okay, so let's start from, let's turn gravity off. So there's no gravity. if they both let go at the same time, then doesn't the monkey just kind of hover there? Right. In that case, you should definitely aim straight at the monkey, right? If there's no gravity, because the banana definitely goes in a straight line. Okay, so that's fine, right? Okay. Now let's turn gravity back on. So now there is gravity. Now the monkey lets go and starts falling and is actually accelerating. So falls faster, faster, faster. Okay. Now the banana, remember, is starts off on this dash line path, on the straight line path, but it's going to deviate from that path, isn't it? And how much it deviates from that path turns out is exactly the amount that the monkey has fallen because they both fallen for the same time in the same gravity field. Right? So if you look at like this is your guiding equation here. Right? I can say eight. Here, I'll replace this x with an h, like a height fall. How the monkey starts from rest. So this v naught would definitely be 0. And then how far the monkey falls as a function of time would just be 1/2 gt squared. Right. So that's how far the monkey falls, 1/2 gt squared. Right. How far the banana deviates from that straight line path, assuming you aim straight at the monkey, is also 1/2 gt squared. If you want to find the exact location of the banana, then that's where the v naught yt comes in. Okay. But the deviation is also 1/2 gt squared, which matches exactly how far the monkey fell. Okay. So now the monkey can grab the banana midair. Okay. There is one more question though, which is, could you vary the speed? Because what if you shoot banana really fast? Like, just make a real shallow parabola. Maybe the monkey catches the banana right out here. Okay, like, what if he kind of walks like, could the, maybe the monkey catches it like down here? Okay, so where exactly the monkey catches the banana depends on how fast he shoots it. But regardless, you should always aim straight at the monkey for that scenario. Right. All right. I think we're ready for a Kahoot. You guys ready for Kahoot? All right, Kahoot. All right, projectiles. All right, pointing brain. Here, pause this video and. All right, we are back recording. Hey, you guys hopped on really fast, which is awesome. So we're gonna do 20 projectile conceptual questions. Here we go. All right, pens on the board if you need it on the board here. A vector, for example, acceleration, is a quantity that has both magnitude and direction. Okay. So like a magnitude is like the number you plug in the calculator, like how big, how much. Okay. But vectors also have a direction associated with them, don't they? Okay, like 30 degrees above the horizontal, something like that, or forwards or backwards or up or down. Okay. 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 Time, by the way, is considered to be a scalar, which it does not have a spatial direction. Okay, so scalars do not have spatial direction. Vectors do. Okay. That's the difference between a scalar and a vector. All right, got points on the board. Got Cole, Gavin, and Kayan. A scalar, for example, mass, is a quantity that has only magnitude, okay, which is the number that you punch into a calculator. It's like how much, okay, but not necessarily a spatial direction associated with it. So like mass doesn't really have a direction. It's just how much. All right. Point. We got Anna, Bruce, Samuel, Cole, Gavin. Suppose a plane can fly 100 kilometer an hour relative to surrounding air, gets a boost 60 kilometer an hour tailwind. So what is the speed relative to the ground?
Oh, oh.
Okay, yeah, I'm gonna draw this out. This is sort of like building up to projectiles, but got to talk about vectors a little bit. So some of you guys got that. Here, draw this out here. So let's do. We've got this plane right here, right? We've got this plane, okay. And the plane can fly 100 kilometers per hour relative to the surrounding air. Don't the jet engines only push against the surrounding air? Right. But the jet engines don't know anything about the ground. They're just pushing against the air. Right. Well, what if the whole air mass is moving in the same direction as the plane relative to the ground? Can I connect these vectors tip to tail? Right, tip to tail right here. So 60 kilometers per hour. Call this a tip to tail vector connection. Okay. And then the resultant is go from the tail of the first one to the tip of the last one. Okay. You guys see that's going to be 160 in magnitude, right, kilometers per hour. Okay. What about this? What if the plane is going 100 kilometers an hour, 100 kilometers per hour relative to the air. But what if the whole air mass is like fighting the plane is going back at like 60 kilometers per hour? What is the plane doing relative to the ground? 40. That would be the resultant. This is the resultant right here. The resultant. I'll spell this out. Resultant equals 40 kilometers per hour. Okay. And what about this? What if the plane's going? So draw a little plane here. Okay. What if the plane's going? Oh, let me do it here. Let's go 80 kilometers per hour. 80 kilometers per hour. And there's a crosswind of 60 kilometers per hour. Right? Now the plane's pointed straight north, but does it actually move straight north relative to the ground? No. Doesn't it also get swept off to the east a little bit at the same time? In fact, what the plane actually does relative to the ground is this diagonal right here. Guess it. Right. So I did a tip to tail connection right there. And here's the two individual vectors, and they combine to make this net effect. Who can tell me if somebody's down on the ground and points a radar gun right at the plane, how fast does that radar gun read? What shape is this right here? All right, triangle.
100 miles per hour.
Yeah, 100 kilometers per hour. Yeah. Is that guys? I just set up a what triangle? 3, 4, 5. Guys, 3 times 20, 4 times 20, 5 times 20. Or you do Pythagorean theorem. Okay. Square root of isn't the square root of 60 squared plus 80 squared kilometers per hour. Same thing. How about this? Guys, how many degrees east of north? Let's say, what is this angle right here? What is this angle? Theta equals how many degrees east of north? 37. Oh, yeah. You guys remember how to do inverse tan of 60 over 80? Could be 37 degrees. Right. Or you could do inverse sine of 60 over 100. It's the same angle. Right. You guys remember that? Right. All right. So there's plane flying around. All right. Back right here. So you guys got that? One. All right. Cold in the lead. What is the resultant of 3-unit vector, 4-unit vector at right angles? Ooh. We almost just did that. 3 units, 4 units at right angles. The resultant is 5 units. Guys, we're talking about a 3, 4, 5 triangle. Isn't that a 3, 4, 5 triangle right there? 3, 4, 5 triangle?
Yeah.
We just made it? Right. 3 up, 4 over.
Like a plug in and I read it's 3, 4, 5.
3, 4, 5. All right, we've got Anna, Bruce, Dara, Samuel, Cole. A plane flying into a headwind loses ground speed. Plane with the tailwind gains ground speed. What about a 90-degree crosswind? Overall ground speed. Yeah, speed relative to the ground. Increases. Right. I'll show you guys. That's also what we just did too. Because here's the plane relative to the ground, 80 kilometers per hour. Here's the wind relative to the ground, 60 kilometers per hour, and it's at 90 degrees. So do you guys see the ground speed? That's this one right here. Right? Here's your ground speed. Right? So somebody down on the ground has a radar gun, points it up at the plane. That radar gun reads 100 kilometers per hour. The plane's instruments think it's only moving at 80 kilometers per hour because that's relative to the surrounding air. The guy on the ground says, no, you're actually going faster than that. 100 is more than 80. Is that some right triangle geometry, right? All right, so you guys figure that out. All right. I got Anna, Bruce, Dara, Cole, Samuel. A ball is thrown into the air at some angle. At the top of the ball's path, its velocity is entirely horizontal. Yeah. Here. Let's take a look. Okay, I'm entirely horizontal. Let me see if I can. Here it is. Here it is. I got. You guys remember this right here in your notes? Which has the first half of the story. Okay. So you throw the ball into the air at some angle, right? And then isn't it true? Its direction is constantly changing, constantly changing, constantly changing. Okay. But at the very top, it's moving which way? Straight horizontal. Straight horizontal. That's the answer right there. Straight horizontal. Right. In fact, how fast is moving horizontally? Did that ever change? 40, 40, 40, 40 meters per second. 40. It's the same all the way. As long as it's a projectile. Right? There's no horizontal acceleration. Same velocity horizontally. Okay? It's all horizontal at the top. Okay? Hi, Gavin, Dara, Anna, Samuel, Cole. A ball is thrown at some angle. In the first second, it moves 5 meters horizontally. How far does it move horizontally in the next second? Yeah, 5 meters, right? So every second it's gaining another 5 meters, 5 meters, 5 meters. It looks like it's going 5 meters per second horizontally, right? And that would be constant. Constant. Right. A projectile maintains its horizontal component of speed because it's not acted on by any. Yeah, horizontal forces. Okay. Guys, are there, if you throw a ball into the air and it goes into a projectile path, are there any forces acting on it? Any forces? Gravitational force, yeah, which would be its weight. Its weight is gravitational force. Okay. Actually, anything that's on a curved path has to have some kind of force on it. Otherwise, it just wants to move in a straight line. Newton's first law of motion. What we're gonna do. All right. So, yeah, but there's nothing acting on it horizontally. Now, you could say air drag, and okay, that would be true. But you guys know in this class we just ignore that, or we call it negligible. Okay, so no horizontal forces. Just keeps going. Got Ella, Gavin, Dara, Anna, Cole. What part of a path does a projectile have minimum speed? Yeah, very top, very top. Okay. So we got the awesome. Okay, just point this out real fast. Okay. Like here, in this example, wasn't the ball blasted at 50 meters per second? And as it goes up, slows down a bit, slows down, slows down. And at the very top, it's only on 40 meters per second. That's definitely slower than 50. But then after that, it picks up speed, and now it goes faster, faster, faster. Okay, you guys remember that too? Like that. All right. Boing, boing, boing. Dara, Kai, Anna, Samuel, Cole. Cannon fires a cannonball horizontally off a cliff at 30 meters per second. How far horizontally does the cannonball move in 1 second? Yeah, 30 meters. Right? Every second, it's going 30 meters horizontally. Right? And that's always true. Now, vertically, it's a different story. Vertically, it's speeding up and all kind of crazy things. But horizontally, it's just going 30 meters every second, 30 meters, 30 meters, 30 meters every second. You guys good so far? Is that it's easier to hit a home run in Denver, Colorado than in Miami, Florida. True, because why? Do players hit the ball harder in the mountains? Is there significant gravitational difference, or is there less air drag due to a thin atmosphere up in Denver? It's the dominant factor here. Yeah, less air. Has everybody ever been up to the mountains, like way up in the mountains? So, guys, what's the elevation of Denver, Colorado?
Like
A mile.
Yeah, 1 mile. Yeah, it's a mile high city. Right, it's up 1 mile. Right, guys, what's basically our elevation down here and by the beach?
sea level.
Yeah, sea level. Right. Okay, so that's like a 1 mile difference, isn't it? Right. If you're ever like running around up in the mountains like a mile high, you can feel it. You feel winded. It's really hard. You're like short of breath. Actually, you guys know a lot of Olympic athletes like to practice like way up high in elevation because their lungs get used to like thin atmosphere. Yeah, the atmosphere is really thin. Yeah, so the balls go further. Yeah. Got Gavin, Kai, Anna, Samuel, Cole.
I live right outside.
In the absence of air resistance, the optimal angle to throw a ball the furthest distance is how many degrees from the horizontal? Okay, so 0 degrees, 30, 45, 60, 90 would be straight up, wouldn't it? That's probably not very helpful. Yeah, okay. Yeah, so a little trivia there. I should have a picture for that. I should draw a picture. Okay. Uh, so yes, it's like 37-degree angle. Okay. And then the ball lands, well, some distance way out here. Okay. But what if you played around with this angle? Because what if I aimed straight 0 degrees? Wouldn't this clunk and hit the ground pretty quickly? Yeah. Okay. What if I aimed 90 degrees? Wouldn't this come down? Bust the can. But also doesn't go has 0 horizontal displacement. Okay. So there's like a trade-off. Like the shallower I aim it, the faster it's going across the field, but for very little time. The closer to 90 degrees is in the air for a long time, but it's not really moving side to side. So it turns out you can prove like the optimal trade-off ends up being 45 degrees. Okay. And again, it's like ideally with no air drag. So if you're in a ball throwing contest with your friends, you can only throw as fast as you can throw. If you aim it at 45 degrees, you'll probably win the contest to throw it the furthest. Yeah, so 45 degrees. Hey. Yeah, all right. You can prove that with calculus. Maybe one day. All right. Cannonball is launched at 30 meters per second over a flat terrain. In the absence of air resistance, it will land with the speed of. Yeah, there you go. 30 meters per second. So it slows down a little bit on the way up. It speeds up a bit on the way down. But equal elevations are going to have equal speeds. Yeah. So as long as you're on a long, flat plane. It slows down a little bit, speeds up a little bit. Same speed for the same elevation. Projectile launched horizontally hits the ground in 1 second. What if it had been launched like twice as fast? Now what happens to the hang time? Right, so you're on top of a cliff, you blast it straight horizontal, then you blast it even faster horizontal. Okay, same time. Right? Isn't that? That's not what we were just doing with versus here it is. Oh, whoops, didn't flip the screen. Here we go. Guys, listen to this concept here. Remember, if the kid just drops the ball, how much time does it take to fall 5 meters? Whoa. 1 second. You guys remember 1 second? Okay. If he throws it horizontally, does it still take 1 second to fall that same height? Yeah, still 1 second. What if he throws it twice as fast? Does it still take 1 second to hit the ground? Yeah. What if he throws like 100 miles an hour? Major league speed. Does it still take 1 second to hit the ground? Yeah, still takes 1 second. As long as he's throwing horizontal or he's dropping it. The vertical motion is identical. Takes 1 second to fall 5 meters. Oh, yeah. So yeah. By the way, that would have been a 5 meter drop. Yeah, that's sick, right? I got Anna, Ella, Samuel, Kai, Cole. Object is thrown horizontally at 30 meters per second from the top of a cliff. What is the acceleration as it is in free fall? Yeah, you guys got it. Yeah. 10 meters per second squared downward, always. Okay. Oh. So isn't that true? Regardless of how fast you throw it, what direction you throw it, guys, as soon as the ball leaves your hand, it is accelerating straight down at whatever the gravity field is. Right. Boom. Right. Moving up, moving down, moving aside, fast, slow. Right. Neglecting air drag. At what point is acceleration greatest for a ball thrown straight up vertically? Throw a ball straight up. When is it accelerating the most? Yes, the same everywhere. Right? Guys, as soon as the ball leaves your hand, it's going up really fast. It's accelerating down at 10 meters per second squared. At the top of its path, it's accelerating down at 10 meters per second squared. When it's coming back down, it's accelerating down. It's always accelerating down at 10 meters per second squared. Regardless of how fast it's going, which direction it's going, none of that matters. As long as it's in free fall, it's accelerating down 10 meters per second squared. Samuel, Anna, Ella, on fire. Kai, Cole, over 9,000. Suppose you can jump 1 meter vertically. If you were on a skateboard moving 50 meters per second to the right, now you can jump what? Yeah, it'd be all the same. Yeah, the same. Right? You get no advantage because that horizontal motion has nothing to do with your vertical motion. Right? Those are independent axes. There you go. Yeah, so you can still only jump 1 meter. Jump 1 meter. All right, we got Samuel, Anna, on fire. Ella, Kai, Cole. When in orbit, a satellite such as a space shuttle. Is the space shuttle free from Earth's gravity? Is it in non-accelerated motion? Or is it simply a projectile falling around the curvature of the planet? Hmm. Ah, yeah, you guys got it. Got it. Right. So, guys, all these projectile puzzles we're doing, one of the simplifications I have not mentioned yet is we're assuming basically a flat terrain. Right. But if you fire something fast enough to the side, actually it works out to about 8,000 meters per second. It's going so fast, it's actually falling around the curvature of the Earth, which, if you're going that fast, that'd be crazy fast, right? But yeah, that's true. Right? Not free from Earth's gravity because Earth's gravity actually keeps it in orbit. If there was no Earth's gravity, those satellites would just fly off into space. And then, well, anything that's on a curved path does have to have a force on it. In this case, it would be its own weight, like a gravitational force. But that's like a future topic. Yeah, yeah, it's like a special kind of projectile, just falling around the curvature of the planet. A little special question. You guys got that too. All right, nice. Ball thrown straight up at 20 meters per second will return to the ground with a speed of 20, 10, 0, 10, 20. Aha! Yeah. So slowing down on the way up, speeding up on the way down, and then by symmetry, it lands in your hands the same speed that you threw it. Okay. All right. I got Bruce, Ella, Anna, Kai, Cole. Are we going for the win? It's a tight race for the win. For the win! A cannon with a barrel velocity 120 meter per second launches ball horizontally from a cliff top. How far will the ball fall in 3 seconds?
Wait, I'm an idiot. No, no, it's not.
But yeah, I lost the
Gravity.
Yeah.
You're under my dad. Don't you great.
Sorry.
5 winners, 45 meters. Here, what's that? Guys, if you launch a ball horizontally at any speed, it doesn't matter how fast horizontally. Slow, fast, or where you drop it for that matter, doesn't fall the same distance in 3 seconds. Right? And that distance that it falls, can you determine that by 1/2 GT squared? Right. But remember, I'm letting this go to 0. Guys, if you blast it really fast to the side and calling this A, say 10 meters per second squared, why am I calling V naught 0 if you blast it really fast? Why is this 0? Okay, let me say it again. Guys, we're setting up an equation here. We're saying how far does the ball fall? That's like it's just placed right here. I'm letting gravity be 10 meters per second squared. We're on Earth. And I blocked it really fast to the side. So I'm going to call V naught 0. Wait, why?
Because the intercept drop is 0.
Because this is in the Y direction. Guys, this is only in the vertical direction. If you blast really fast to the side, it has no initial vertical component of velocity. Okay. And then, guys, let's run the numbers. 3 seconds. What's 3 squared? 9. What's half of 10? 5. What's 5 times 9?
45.
45. 45? Wait a minute. 45? Is that in 3 seconds? It'll always fall 45 meters? Yeah. As long as you either drop the ball or you throw it horizontally, that's always going to be true. Yeah. All right. So let's see. Who won the Kahoot? Who won Kahoot?
7 minutes.
Kahoot! With the bronze, Bruce! With the silver, Kai! And the gold, Cole! Right, nice job. Nice job. Right, so we got a few minutes. Let's do some more of these projectile puzzles. projectile puzzles.
Do online practice at home.
Yeah, I can do that. All right. Oh, whoops. Sorry about
Mr.
that.
Griffin, is this a test?
Yeah, there's gonna be a quiz on Friday.
No, like all these questions, they're the
Is there quiz
ones
gonna be like this
basically
too?
like this.
I may pick a couple of those off for
Okay.
the quiz. Yeah, there might be a couple of those on there. I forget exactly what I put on the quiz, but yeah, you should put at least a couple of those on there. Yeah. All right, so we're on this page. All right, so I did a couple of these on the left. I did a couple of these on the right side. The left side's like a starting on a cliff. The right side's like on a giant plane, angled cannon. Okay. Now the ones on the back are like a hybrid questions. You guys see where yes, there's a cliff, but there's also an initial incline angle. You got both going on. No, these are all the same scenario. They're just different numbers, like different cliff heights and different cannon speeds. Okay, you guys get that? But they're all like the same process. Is what I mean, the same process. Okay. Okay. And the left example, I was really helping you out. So if you follow these step by step by step, if you follow all these steps in order, it should lead exactly to the correct answer. Okay. The like this one on top right is a little more open ended, but it's the same process. So here, I'll do this one on the top. Well, here, I'll just one on the bottom right, just to show you that I am getting the correct answer. So a little multiple choice here. Okay, so we all have different papers. Mine says, okay, 9.8 meters per second squared downward. Okay. Keep in mind, if gravity's pulling down, but you're blasting sort of upish, is there going to be a negative sign somewhere in the math? There has to be, because it's like up versus gravity's pulling down. Okay. I have there's the height of my cliff. I got a 67 meter tall cliff. And I have an incline angle of 30 degrees from the horizontal. So that's that angle theta right there. And my cannon blast speed is 101 meters per second. Okay. Good thought. Okay. Now with all of that, there is some distance out here. Like how far out does the cannonball go in meters? You guys get that? Okay. So I'm gonna copy paste that scenario right here. Because if you're really lucky, you might have the same numbers I do, but I wouldn't count on that. It's not very likely, but maybe. And we're going to solve this thing. So here's my cannon, aimed up at 30 degrees from the horizontal. So this angle right here is 30 degrees. My blast speed, I'll call it V blast, is 101 meters per second. I'm just reading that straight from the paper. I gave you guys the cliff height. My cliff height, I'll call it H, is 67 meters. And what we're calling G, Earth gravity, is 9.8 meters per second squared. And that would be, of course, downward. Keep that on too. Okay. And so first thing you do is you split this blast velocity into components. You say, well, how fast across the field is the cannonball going? And how fast was it initially going upward? You see I dashed off those components? It's that. So this right here I'll call V sub x. And isn't that equal to 101 meter per second times what? Sine or cosine at 30 degrees? See, it's adjacent to 30 degrees. That makes it what? Cosine. Yeah, cosine at 30 degrees. Okay. Okay, therefore, this, I'll call this V initial in the y direction, should be 101 meter per second times sine of 30 degrees. Is that true? Okay. I'll go ahead and get numbers as we go along. It's probably a little easier to work with numbers than variables. Cosine 30. Okay. So this would be 87.47 meters per second across the field. And that's always true. And this one up here, if I scroll over, pop in a sign, this is 50.5 meters per second. But keep in mind, that's only true when the cannonball is leaving the barrel because gravity immediately starts pulling down and that starts changing. Okay. So the path of the cannonball probably does something kind of like that. That's basically a parabola, right? Okay. And I want to know what is this distance x right here, right? I want to know the distance x. You guys hear that? Okay. Well, we did the first step already. Is here's how fast, well, strictly up initially, and here's how fast across that it's always going. Okay, you guys got that? Okay. Next thing, I need to know how much time this takes. Now, here's probably the trickiest step. I only have 2 minutes, so I'll show you guys how to do this. Can you guys set up y equals v naught y t? I'll say minus half g t squared. Okay. So No, guys, if I'm calling down negative, which I did right here, doesn't this cannonball overall move down? So should I say 67 or negative 67 for the height? Negative 67. Of course, it's meters because it's going down. I just called down negative. That's why I'm calling it negative. Right? It overall moves down. So this would be positive 50.5 meters per second times some time I'm solving for. Then minus 1/2, 9.8 meters per second squared. And then t I'm solving for again squared. Okay? Guess that. Now, you're solving for this t. Here's t squared. Here's t. Here's a number. Can I add the 67 over and get this like in a quadratic equation form? Like ax squared plus bx plus c equals 0. Okay. So I'm just going to write the word quadratic because I'm really short on time. Quadratic. Okay. Then I'll get t equals some number of seconds. You guys got that? It's going to be a quadratic equation. Can you guys see that? Okay. After that, the very last step goes like this. How far it goes across is equal to v sub x times t. And the v sub x is this 87.47 meter per second on my paper. So I'll do 87.47 meter per second. And I'll multiply that by whatever I get for this t that comes from this quadratic equation. That'll tell me exactly how far it goes in meters. Yeah, that's the whole thing. All three scenarios on the back are that same process. All right, and that is a wrap on today.